Alright guys, we want to take a deeper look into what the Fundamental Theorem of Calculus Part 1 is telling us about the function f and its antiderivative. Number one, what it tells us is that any continuous function, so if f is a continuous function on an interval from a to b, then it absolutely has an antiderivative on that interval from a to b. So every continuous function has an antiderivative. Number two, not only does it have an antiderivative, but here's a formula for it. So the antiderivative is given by the integral from a to x of the function f of u du, where the u is just an integration variable. So let's start by remembering what it means to be an antiderivative in the first place. And so antiderivatives obey the property that given the function f, so f of x itself, the antiderivative of f, or an antiderivative, it could have many, an antiderivative of f is a function for which the derivative, in this case of g of x, is equal to f of x. Okay? And so another way to write down this Fundamental Theorem of Calculus Part 1 is that the derivative of the formula for g of x, so the derivative with respect to x of the integral from a to x of f of u du is just equal to the function f of x itself. Now let's take a closer look at a couple of pieces of information here. Number one, the variable in the derivative matches the upper bound, the variable in the upper bound of the integral, and nothing else. So there's no other x's in this equation. Number two, the u over here in the integral, that's just the integration variable itself. So that we have to put that there because we don't want the x's anywhere else in the integral. And number three, the output here, after you take the integral and then take the derivative, what you end up with is just the function f of x itself. Okay, so this is very useful because it gives us a way to represent the antiderivative of any function f that's continuous on an interval from a to b, even if we don't have a formula for that function itself. So even if it's not a function that we know how to write down a formula for its antiderivative, we can write down at least this integral formula for it. The other nice thing is that we know what it means to be a definite integral geometrically. So we can now think about what is the antiderivative of f doing to f, or to the function, to the graph of the function f, to take away the derivative in some sense. And so for that, here's a graph of a function on an interval. It's a pretty nice looking curve, but we don't have a formula for it. We can still describe what the antiderivative is doing. And so remember from the last slide, the antiderivative of this function f is the integral from a to x of f of u du. And we know that the definite integral, this part right here, this measures the area under the curve between x equals a, and in this case x equals x. So what the heck does that mean? Well, this number x has to be between a and b, so let's say maybe x is right here. And this x is a variable, so this could move around in the domain over here, between a and b. It can't go outside of b, and it can't go outside of a to the left. But it can go anywhere between a and b. And then this function g, well, it's measuring the area that's bounded between the x-axis and the curve f of x. And so it's measuring the area of, for this function, this piece right here. Okay? And so the area of this portion, this is the value of g of x. That's the area underneath the curve of f between a and x. If we try to move around the x, maybe x goes this way. And so for the function I've drawn, the curve is always positive. So if x goes this way, moves a little to the left, g of x is going to be a little bit smaller. The area is going to be getting a little bit smaller. If it moves to the right a little bit, the area is going to get a little bit bigger. It's going to have to add on this orange portion here. Okay, and as it goes all the way from a up to b, it's going to fill out the entire area underneath this curve. So that's what it means to be an antiderivative. The antiderivative is just gradually adding on area underneath the curve as the variable moves from a toward b. All right, well, again, this can be very useful. Number one, it's nice to be able to visualize what calculus is doing to our functions without having to write down a formula. And number two, it might be useful for functions that we have no idea how to find the antiderivatives of. So this curve is very important in statistics. This function, I should say, is very important in statistics, where its graph is something called a bell curve. And we won't get into the statistics right now of why statisticians care about this function so much. But let's just think about what the graph of this has to look like. When x is equal to 0, so when this crosses the y-axis, when x is 0, this is e to the 0, which is 1. So this has a height of 1. when it crosses the y-axis. And as x gets bigger in either direction, it's going to be symmetric. And e to the minus a number is getting smaller, right? So this, as x gets bigger, approaches 0 in this direction, but it never gets there, so it's got a horizontal asymptote. And same thing in this direction. It's supposed to be symmetric, so you can critique my drawing if you want. But this is what's called a bell curve, and again in stats. And it's an important question to try to ask, what is the antiderivative of this function? So does this have an antiderivative? And of course, just by looking at the graph, we can tell that it's continuous, so it must have an antiderivative. That's what the Fundamental Theorem of Calculus Part 1 tells us. But the question of what is that antiderivative is actually really hard to answer. It turns out that this has no simple function that we can write down like a formula, a nice formula, for which it is the antiderivative of this function. However, we can still understand what the antiderivative is trying to do, right? So the antiderivative, according to the Fundamental Theorem of Calculus, is that g of x is equal to the integral from any number. This is defined everywhere, so let's just do it from the origin. But from 0 to x of the function e to the minus, and then we have to swap out the variable here, so e to the minus u squared du. And remember, we now have some geometric intuition about what this antiderivative is trying to do. It's trying to measure the area underneath this curve from the origin to the input value x. So whatever that area equals, this antiderivative, that'll be its value. And instead, in statistics, again, that's what's extremely important to them. They care a lot about the area underneath this curve between certain points. Okay, so yeah, this is a hard one. We don't know how to write down an antiderivative for it, but it actually happens to be very useful. And so to kind of alleviate that problem, that potential problem, the Fundamental Theorem of Calculus comes in and helps us out. And so when you get to a little bit higher level stats or a little more calculus, you will see this idea again. And your teacher might not tell you that that's the Fundamental Theorem of Calculus doing its work, but you will remember it. So don't forget.